Let's wait for a couple more minutes for more people to join. Okay, all right, let's get started. So this is the second lecture of wind energy. So a brief review of what we did last time, right? So last time we covered, the wind power, it depends on height and different terrain, right? And then we look at basically how to think about speed-power relationship. So last class was about, if you're at a certain height above ground, the wind is blowing at a certain speed, how much power is there? How much mechanical power is there in that moving mass of air? For this class, our goal will be to look at the design of the turbine and design of the blades to see how much power we can extract from this moving mass of air. So that's the idea. And also as an announcement, the homework 1 is out. Homework 1 is posted on the class website. It's a mixture of review of circuit analysis, review of power electronics, combined with some questions about what we covered on Tuesday and what we'll cover today. So this is due next Wednesday at midnight. It's due Wednesday at midnight. So I have an office hour Friday afternoon. Yao, the TA, she has office hour Wednesday afternoon, next Wednesday. So, you're encouraged to come to the office hours. Also, you can email us, any question you may have. Okay. So if you look at the homework, sorry for posting, last minute before the class. If you look at the homework, the last question is a question that the graduate student should attempt, right? You're expected to attempt the last question. If you're an undergrad student, if you're taking 451, then you can treat that as a bonus question. Okay, so in many homeworks, it will be like this. There'll be one question that's very open-ended. And so that's sort of how we differentiate 551 versus 451. Any question about this? About homework process? Okay, all right, yeah, so now you can talk among yourselves, right? If you run into, if you have trouble doing the homework, that's fine, right? Just as long as, again, you write your own solution, then that's okay, right? And I'm sure you have all seen an email from Professor and Chair Eric Clevens about other things going on. So And last quarter, I taught a class right after the November election. So all our hope is we'll teach class at normal times. But obviously, there are other things going on, and you may be distracted. You may feel fine. But if there's special considerations, or there are considerations you have, or there's deadline extensions, please let me know. Okay, please let me know. Okay, so if no questions, then let's look at what we'll do this class, right? So this class is about, you can think of as turbine design. Design, okay, turbine design is how do you make a sort of the physical turbine, and what does that have to do with how much power you extract from the powering wind, right? So a turbine, if you look at what a turbine looks like, so if you look at it head on, and basically if you look at head on, the turbine is, you have a tower. So let's draw this as a tower. You have turbines like this. You have the turbine blades like this. So this is the tower above ground, and these are the blades we have. So if you look at the blades at the cross-sectional area, then basically it's airfoil, right? So it's exactly how an airplane wing would look. So this is called airfoil. The aerodynamics of airfoil can be quite complicated. Okay? We are not going to go into that much depth. So for us, what airfoil look like, there are basically two things that we care about airfoil. Right? One is we care about the center of gravity. So we care about center of gravity. Center of gravity is how we think of where the airfoil is. Okay, so we're going to summarize the airfoil basically by center of gravity. Okay, so how long is a blade? Well, the length of blade is the center of, how long is from the hub to the center of gravity. Right? So these are the ways we'll think about this blade. Then another thing that we'll care about in this blade is the angle, is the pitch angle. So whenever you have airfoil, right, you can have airfoils that have different angles with respect to some reference angle. So we'll care about this kind of angle. So we'll care about the angle the airfoil makes to a reference, let's say ground. And then we'll care about sort of center of gravity because that tells us the location where the airfoil is. Okay, so this is our airfoil. I will look at basically a bunch of physics associated with this airfoil. So if you look at this, right, if we look at this, then the basic theory of airfoil is following. You have a leading edge and a trailing edge. Air is coming in this way, on the leading edge. We have upper chamber and lower chamber. Upper chamber means the surface, you can think of the surface above, and lower chamber is the surface below. And a popular theory is the air will break up into two streams, right? Because the travel distance on top is longer than the travel distance on the bottom. This creates a pressure difference, and the pressure difference, right? And the pressure difference basically creates lift. Pressure difference creates lift. And indeed, if you read the reference book we have, Wind Energy, and we have this quotation out of this textbook, right? So the air molecules separate at the leading edge, and they meet at the trailing edge at the same time, right? So we have a speed difference because the air on top has to travel faster than the air below, and that creates a pressure difference. So this pressure difference basically creates something called, the Bernoulli's principle, where because you're faster on one end, slower on the other side, this pressure difference creates lift. The lift is created this way to the Bernoulli principle. Okay? So this is similar with wind turbine. So you have a wind turbine. Basically, we're doing is, so this is my turbine. Wind is coming, right? Coming this way. Then if there's a lift on this turbine, then I turn like this, right? So you have a lift on the turbine. Since this end, let's say it's fixed, and the lift becomes a turning motion. And this turning motion can turn the generator, and the generator can generate electricity, right? So this is the, this is often what you'll see in the theory of airfoils and how does a blade turn. Right, so this theory is, in some sense, obviously incorrect. Okay, so the good thing to know about this theory is obviously incorrect. So so for the folks who taken 351, you probably heard this story. Let me remember why this is incorrect, or why this Bernoulli principle has very little to do with airplane flight when turbines turning. Anybody remember the reason? Right. So what's wrong with the story I just told you? What's wrong with the story of I have, molecules separating, creating a pressure difference, and the pressure difference pushes the blade to have lift? Anybody remember this? Anybody remember the reason why this is wrong?
I thought that the pressure or the lift was created by the angle at which it comes off the top of the airfoil, causing a force upward. That's what one of our professors said.
Right. So the reason this is wrong, right? So it's fairly simple thought experiments are pointing to this is not quite correct, right? Because now most of us probably made paper airplanes before, right? So if you make a paper airplane, the wings, the airfoils are completely flat, right? There's no curvature, there's no difference between the length above and below the wings of a paper airplane. Paper airplane flies fine. Okay? It can fly a fairly long distance. However, if this theory about lift is correct, then paper airplane has to follow a projectile motion. Right? So if the only lift comes from the fact that air has to travel different distances, there's no reason paper airplane flies. And more so, if you have let's say you have a normal airplane, if you turn it inverted, so if you fly upside down, the airplane can also fly. It actually flies, it's not as efficient, can fly for a fairly long distance. It's not, you may be very uncomfortable, but there's nothing wrong about the plane flying that way, right? So those two examples tells us it's really not about Bernoulli's principle. Right? It's really not about Bernoulli's principle. It's maybe there, but there's very little impact on the lift. So the reason is, and also another reason is what does air molecule meeting as a trailing edge mean, right? So these are molecules. Why do they know? How do they know to meet at trailing edge? Right? There's nothing. And indeed, if you put this into a wind tunnel, they don't meet at the trailing edge. You can observe it, and there's no reason they meet at the trailing edge of the airfoil. So the reason this generates flight, as somebody said, is basically you have an angle, right? You have an angle. And what happens is if you have airfoils in an angle, then because air is a viscous fluid, so air tends to hug the surface of the airfoil. So if air hugs the surface of airfoil, there is a downward force. Right? So there's a downward force. Right? So downward force from air. Okay, so you're bending air downwards. So this is air going downwards. Then by Newton's third law, then you have to push, airfoil has to go up. Okay, so you're pushing the air down, the air is pushing you up. And the reason is because air tends to hug the shape of the airfoil. So the shape is important. This is not saying the shape of the airfoil is not important, right? Shape of the airfoil contribute quite a bit to how efficient lift is generated. But the reason they contribute to the efficiency of generation of lift is you want to bend air in a more efficient way. Okay, you want to bend air in a more efficient way. So that bending of air comes from the shape. And if you bend it very efficiently, you generate more lift. Right? But it's not necessary to have this shape to generate lift. Right? So lift is basically comes mostly from Newton's third law. Okay? So that's why normally everything has to have an angle of attack. Okay? So you cannot be being completely aligned with the direction of wind. Typically, you don't generate much lift. If you have an angle of attack, you tend to generate more lift. Okay, so because this angle can create better lift, you bend the air down, downwards. Okay. Right. So any question with this?
I guess maybe just a quick clarification. So the air that's pushing the airfoil down, so there's air on top of the airfoil, right? And it's also pushing the airfoil downwards. But I guess that force is not as strong as the force exerted by the air under the airfoil. Is that correct?
So in net, the air is bending down, right? Because the net force air is bending down. So in net force, then the airfoil has to go up, right? So
okay.
Yeah, there's nothing. So the air is not pushing it down. Basically, you're pushing the airfoil is pushing the air down. So then the air has to push the airfoil up. Right? So that's the action and reaction.
I have a question.
Yeah, go ahead.
So, but at the same time, the airfoil actually also pushes the air like on the top of it. So, which means the air on the top of it will also push the airfoil down, right?
Right. So that's why it's often important to have an angle, right? Right. So if you look at the trace of air, right? So you look at this sort of traces, and this goes up, then goes down, right? So what you want is in the net force is going upwards. You have a net lift when you look at the entire object, when you look at the entire airfoil. Right? You have, so the force acting across the airfoil is definitely not uniform on the airfoil. But what you want is if you look at airfoil at its center of mass, then the force acting on that center of mass is pushing up.
Okay, so it's actually an important matter of the shape of the airfoil.
Oh yeah, the shape is tremendously important.
Okay.
The shape is tremendously important. I mean, if you design airplane, hundreds of millions of dollars is spent on finding out the shape of the wing, right, of the airplane. So the shape is important. And also you can have an angle attack being negative, right? So if the airplane, if you go down and want to descend, then of course you bend downwards and you descend. Right? So it can, right? So depending on the angle of attack, depending on what your angle is, you can generate, lift can be positive or you can go downwards. So the shape is important, but the importance of the shape does not come from Bernoulli's principle, right? The importance of shape comes from how exactly does the air flow around the shape, right? How much the air envelope gets bent downwards.
Can I ask a question, please?
Yeah, go ahead.
So there has to be some component of movement in this though, right? Like, because if you were just like to place a paper airplane in a room, gravity would take over. So
right.
How much does the air have to be moving relative to the airfoil?
Right. So if you want to you want the plane to fly, right? You have to provide thrust, right? So basically, you want the speed of the air coming to the airfoil. So if you take airfoil as a reference, the speed of air hitting it has to be high enough, right, to generate enough lift. So the amount of lift you generate is not proportional, but depends very much on the speed of incoming air hitting you. So there's two ways to generate speed, right? In a wind turbine, you do nothing. You sit there and for air to come at you. Whereas an airplane, you provide the thrust. So there's a high speed and you get pushed out.
Okay, thank you.
Right? Yeah, so that's why in a paper airplane, you have to throw the paper airplane. Right? So throwing the paper airplane gives you this initial lift. But if you drop it, it will go down like this. So that's the idea of wind turbine. Any other questions? Right, so this is one of the reasons we decided not to use the book, right? So it's not, the book is not very good. Basically the book, this is airing the book. The book uses Bernoulli's principle as a reason for turning of wind turbine blades, which is not quite correct. Okay. All right, so this comes down to, this is related to the other question. Basically, to generate this lift, I need air to move at a high speed reference to my airfoil. So this is you basically have a drag term, you have a thrust and drag term. And you want the thrust to be bigger than the drag to increase speed. So this is for airplane to fly. If you go forward, there's a force going forward, but you also have a drag on the airfoil, and this is the flight of the airfoil. So more information. So NASA does a good job with this. You'll see a lot of nice simulations done by NASA. I guess NASA was a little bit disappointed on the wrong theory of flight out there. So NASA has this bunch of videos. You can look at it and explain sort of this in more detail. All right, so for us, what we'll do is we're not going to into the detail of fluid, we're not going to look at the fluids all that much. So basically our goal is to get an empirical equation relating the speed of wind to the mechanical power we can generate out of the turbines. Right? So remember, our goal was, we know at a given speed, we know the wind power density. Right? So that's the power in wind. But that doesn't mean we'll get all of it when we convert that to electricity. So the goal is to take that wind, to take, get a way to understand how much of that power naturally in wind, how does that convert to the amount of mechanical power, then to electrical power. So that's the goal for the sort of rest of this class. Right, so now we're gonna look at airfoil. Again, we're gonna assume that wind is blowing towards the leading edge of the airfoil. Right, and then for us, since for a wind turbine, the airfoil is fixed at one end, all we want to know is how much this force is. So this force is a force that turns the turbine. Right? So this force turns the blade. Right? So this is the force that turns the blade. And larger the force, the more power I have from turning those blades. Okay, so this force is, basically you can think of the force as the pressure, the net pressure on this airfoil multiplied by how large this airfoil is. So that's one way to think about how this force is generated. Right, so we're gonna summarize, we're gonna think of the lift action as coming from a pressure, even though it's really Newton's third law. And then we have the equation that the total amount of force acting on the airfoil is the pressure difference multiplied by how big the area is. And that creates a sort of turning motion on the blades. Okay, so that creates a turning motion. Okay, so, and for us, again, since this is only motion we care about, right? So our airfoil is not gonna move, in and out of the plane. all it's gonna do is to turn, then we only care about the force that's perpendicular to the surface of airfoil. So others do not generate power for us. Any questions about this? Okay, so as we said, an important number, an important variable is the angle of attack. Right, this is angle of attack. Angle of attack is the angle the airfoil makes with wind. Okay, this is alpha angle. Okay, so the angle of this, so this is the angle of attack. Right, again, the terminology comes from airplanes, right? So you have angle of attack is how much you lift the airfoil. So the angle of attack basically determines how much this aerodynamic force we have. Okay, determines how much aerodynamic force we have. So a smaller angle, right? So there's a trade-off between the angle of attack and lift. There's always a trade-off between angle of attack and lift, right? So when in this case, when alpha is 0, then this is all of this force generated is lift, right? So if the angle of attack is 0, then everything is lift, right? If the angle of attack is positive, then sum of the force is lift, but the total amount of force is larger. Okay, so total amount of force is large. So if you have an angle of attack 0, wind blows comes in this way, then everything basically is perpendicular. So this is turning the blade, right? This is turning the blade. But if the angle of attack is positive, some of this force is basically wasted, but you have a larger force in total. So there is by changing angle of attack, you can change the force. And there is a sort of optimal angle of attack, right? There's often an angle of attack that sort of maximizes the amount of power you can generate. Maximum amount of power you can generate. And the way the wind turbine changes the amount of power it generates is basically by changing the angle of attack. Okay, by changing the angle of attack it exposes to. Right? So again, so if you have operating a wind turbine, and if you don't need your maximum power, then you don't operate as the angle of attack, as optimal angle of attack, right? By changing the angle, you can change the lift force. And changing the lift force changes the power you generate. So that's why you can stop a wind turbine from generating power, even when the speed of wind is very high. You basically pick an angle of attack such that you have no lift. Right? Such that you have no lift, then you generate no power. So wind power the power a wind turbine generator cannot be increased past its capacity, but can easily be decreased by changing the angle of attack. And so we'll see more of this in detail. Right? But the basic idea of angle of attack is this is a control variable we have to control the amount of power that's being generated. So we have this variable. Okay. So this summarizes, right, how we break up the aerodynamic force into two components. Right? So the lift is what we want. The drag is sort of wasted for us. Right? So the idea is to sort of maximize the amount of lift we have. Right, so any questions so far? Okay, so turns out the exact equations for lift and drag is very complicated. And the actual equations are complicated. So we'll basically cheat. We'll do a cheat to write down the equation of the forces. So for us, we'll basically write down the equation of force throughout two coefficients. Right? So so you can think of, so half delta AF. So if you look at this equation, right? This is the amount of force we have in a moving air, right? This is the amount of force we have. Then we're going to scale them by some coefficient, that determines how much of this force goes into lift, how much of this force goes into drag. So this is our way of capturing the amount of force we'll have. So if we can measure the air speed, incoming air speed, then depending on the angle of attack, a fraction of it gets converted to lift, fraction of it shows up as drag. So we have this two depends on, of course, they depend on the alpha, right? So these are functions that depend on the angle of attack. And then if you know the angle of attack, you can read out the coefficient, you can determine the lift force, for example, that you want to calculate. Any questions about these two equations?
I have a question.
Yeah, go ahead.
Could you repeat what you were saying about if alpha is greater than 0, the total force is larger?
Oh, okay, sure, yeah, sure. So if you look at you look at this angle alpha, then this angle alpha basically, so let's see. So you have let's say you have two different angles of attacks here. Then for the two different angles of attacks, for this one, air does get bent downwards, but sort of relatively small. The motion of air may be relatively small. So the force could be smaller. Then if you look at when alpha is larger, then if you look at the motion of air, basically you have air coming in this way, go through the airfoil, then gets sort of bended a lot downwards. So there's a larger force exerted on the air, then the air pushes back harder on the airfoil. So this angle of attack, by chaining this, changes the lift you have, changes the amount of total force you have, right?
So you're saying that like the red arrow, like
right.
the force that's represented by the red arrow is what's being increased?
Yes, so this should be longer. So let me be more, so this is a longer arrow. So this is a larger net force on this, yes.
Okay, thank you.
All right. Yeah, so this is sort of similar to airplanes, right? So you change the angle of attack for airplane, you change the total force. Right, so for us, we'll summarize this as basically two coefficients that depend on alpha. We will not compute those coefficients in any first principle way. So the way this question will show up, for example, in your homework, is you'll be given the equation of, let's say, CL as a function of alpha. Then I'll say, okay, suppose alpha is 10 degrees. Now figure out what the lift force is, right? So the way it shows up is we'll have an empirical equation for the lift coefficient, and we build this empirical equation, let's say through some experiments. And then by looking at the data, we can put in a table the coefficient at different values of alpha. And we'll usually just read out from that table. So we'll build an empirical equation. Okay, and so all wind turbines are tested. So if you build a new turbine, you build new blades, you actually test it in practice to read this kind of numbers out of it. So see, how does this coefficient depend on the angle of attack. Okay. Right, so of course, yeah, so these are the names of the coefficients. Again, we'll be just given we're just given the numbers for these. So this we done. right? So this shows sort of different, a picture of different angles of attack, right? So you can get negative, okay? You can get negative lift. So this is negative lift, right? You can get negative lift because if you have a negative angle of attack, right? So it's possible to get negative lift. Right? It's possible to turn generate force downwards compared to upwards. And then you can turn your airfoil in such a way that it's all the forces completely goes into the draft. So both are. By turning this angle, everything's possible. Right? So angle of attack does not have to be positive. So when you look at, again, the turbine turning, it can, so yeah, I need a three-dimensional thing. So yeah, so imagine a turbine turning, basically by changing the angle. So let's say wind is coming in this way, and this is my angle of attack. By changing the angle of attack, I can change the turn speed. I can change, it's possible to change which direction you turn. Or if you put it completely perpendicular to the air, then you basically everything is drag and you don't move that much. So you can lock the turbine. Right? So you can lock the turbine mechanically. So all this is possible, and this is actually the main control mechanism of a wind turbine, control how much power you generate. This is the main control mechanism. Okay? So this is we're going to change different angle of attack. And again, if you plot the angle of attack versus lift, you get something like this. So it'll be an angle where you have no lift. There'll be an angle where you have maximum lift, and there'll be a sort of everything in between. So for wind turbine, we basically want to operate in this region. Okay, so this is the operating region. So why don't we operate at sort of very close to the maximum alpha or to the optimal alpha that generates the maximum lift?
Run the risk of stalling.
Right, you run the risk of stalling. So here, this is turbulence, right? So here you actually becomes difficult to operate the turbine when you have turbulence. Right? So you want to avoid having turbulence. So to avoid having turbulence, there's always a safety margin. There's always a safety margin to avoid turbulence. Okay, so we want to avoid this, and that's the reason we have basically want to operate away from the angle of attack that actually give you maximum lift. So this is a phenomenon we see very often. As when you hit the maximum lift or maximum power, often is sort of very sensitive to the operating point. So this is also the case. Okay. So this also answers the question, why does wind turbine have 3 blades? Okay, so this also answers that question. Why does it have 3 blades, right? So for a wind turbine, if it has too many blades, if it has, let's say, 4 or 5 blades, what happens is once a blade passes through a region, you create turbulence. And if the next blade comes in and hits a turbulence, that's very inefficient. That may damage the blade. So you cannot have more than 3 normally. Okay, so if your blade is sweeping through the region, will create some turbulence after pass through the region. And the next blade cannot come very quickly into the same region. Right? This is sort of similar to this, you want to avoid when the air is very turbulent. You want to avoid this kind of case. Okay, so in case you have the questions, why don't we put 10 blades on a turbine? That's the reason why we cannot put too many blades. So when you operate everything, you basically want to avoid turbulence. You want a smooth operation. Right. So any questions?
I was curious what factors go into the safety margin?
What factor goes into the safety margin? So there's different factors. One is your actuation capability, right? How fast you can turn the blade. So if you have good sensors and you have fast actuation capability, you can operate closer to the maximum. Right? You can operate closer to maximum lift. As You're worried if you're too close to the maximum, if the wind changes a little bit, right? Let's say the wind direction changes a little bit, and you're afraid that will push you over to the stall region, to the turbulence region. So if you have very good sensors, if you know the direction the wind is coming in, and you can pitch the blade fairly quickly, then you can be closer to the maximum lift region. So that also has to do with the exact shape of the blade. So some blade, you have a wider region of operation. Some blades, you have a much narrower region of operation. That's a lot of aerodynamics going to it.
Thank you.
Yeah. Yeah, so this actually, so if you look at the turbine design, look at blades, there are a bunch of control mechanisms around it actually. So it's a fairly complicated system to actually make it work, especially for large blades, especially when you have this sort of, 8, 10 megawatt turbines, and there's a lot of machinery associated with it. A lot is to do this sort of real-time control. And measuring wind speed is by no means trivial also. It's not always easy to measure the direction, for example, exact direction of wind coming in. So normally there is a somewhat safety margin. So let's do an example, right? Let's do an example to see how this is used. So this is a quite typical example, quite typical. Right? So basically what this says is a 3-bladed wind turbine. All of our wind turbines will be 3-bladed. And the wind exerts on each turbine the aerodynamic force. So this is the total force we have, 2,000 newtons. Then we pick some particular angle of attack to get a coefficient. So alpha is 0.9, sorry, not alpha. The lift coefficient. Right? Some angle attack, we get this lift coefficient. And then if the center of gravity of the blade is 30 meters from the hub, we want to compute the torque. Right? We want to compute the torque generated by the blade. Then we want to translate that torque into power if the blades are 30 RPM. So this is our question. So if you look at the figure, this is the hub. We have a blade. The center of this is 30 meters. And we know the total force on this is, total force is 2,000 newtons. We want to figure out how much torque and how much power, mechanical power is being generated by this blade. Right, so any thoughts on, right? So what do we do to solve this problem? Right, so the first step is to convert. Right, so look at how much lift we have. Again, for the only force that translates into mechanical power is the lift force. So this is 0.95 times 2,000 newtons. This was 1,900 newtons. This is our total force. Then how much torque do I have? So if this is a force, right? So I have a hub, I have some blade, and I have a force that's turning the blade. How much torque do I get out of this? Remember the equation relating force to torque?
Is it the sum of the lift times the distance from the center?
Right, so this is the lift, right? So this is the force times this how long your blade is, right? So to the center of mass, right? So this is, so torque on one blade is the force times distance, right? How long this is. So this distance is 30 meters. Distance from the center of the hub. From the hub to the center of the blade. So this is multiply. So this is 900 times 30, right? Then the total torque is 3 times the torque on each of the blade. So here we get 171 kilonewton meters. So this is the total torque we have. Total torque we have on the blade. But how do I translate this to power? How does the torque, mechanical torque, translate to mechanical power? Anybody remember? It has to do with the rotation speed, right? So the rotation speed is given. It has with something to do with the rotation speed. Anybody remember what the equation is? All right, so if you don't remember, the equation is the angular rotation, the angular speed times the total torque times the total torque. Right, so the torque times how fast you're going determines the power. So the angular speed. So the tricky thing about this kind of questions, you have to convert the units, right? So here, omega is in radians per second. Whereas for natural sort of rotational speed, we tend to measure things in RPM, rotations per minute. So that's just a more natural unit of measurement. But the equation needs to be in radians per second. So to convert this to radians per second, this is 2 pi times your rotation speed, right, in RPM, divided by 60. Right, so divide by 60 to get to be per second, times 2 pi to get a radian out of this, then times the total torque we have. This is 2 pi times 30 over 60 times 171 kilonewton meters. And if you put everything together and work out the units, this will be 537.2 kilowatts. So a sort of decent sized turbine. Okay. So we will use this equation. Actually, these two equations are used quite common for us. The one to remember is it's going from force to torque. Another to remember is going from torque to power. We'll use this to quite a bit in this week and next week. So if you're in the refresher, you can look up some textbook or just remember these two equations. Any question with this example? Okay, so if not, let's take a break then. So let's take a break until 1:30. And then we'll keep looking at this sort of mechanical power generated by airfoil. Okay, so let's break until 1:30. All right, so let's get back to this. So there's a question on the chat, does the weight of the blade not matter? The weight of the blade definitely matters, but our analysis is not detailed enough to capture the full impact. Basically, that is rolled into the speed of rotation and also the lift coefficient. So it's rolling to those two numbers. So what determines the speed of rotation of the blade is the shape of the blade, the weight of the blade, the speed of incoming air, and all those kind of things. So this sort of complicated factors. So for us, we'll basically summarize to the speed of rotation and the total force, or the lift coefficient. So yeah, so definitely matters, but to get to that requires a lot more work. Right, to sort of compute the speed of rotation is quite a bit of work. So often we'll just look at what the speed is. And also in practice, you do this by actual observation of the speed. Right, so there's not much. So when you in practice, you basically observe how fast your turbine is spinning, and then do sort of control from angle of attack. Right, so again, next is this slide, just a reminder that angle of attacks cannot be too large, right? So the main thing is to avoid stalling. So stalling is really bad. So the main thing, often when you do this control, you really want to stay away when the blade will stall. That will create physical damage to the blades. Right? So you want to keep the angle of attack reasonable to avoid this kind of a lot of turbulence as it stalls. Right? So now let's come back to the speed of wind, right? We said wind speed has a big impact on the amount of power we generate, right? Wind speed is the force, relates to aerodynamic force, right? But whenever you talk about speed, it has to be always clear the reference we're measuring to, right? Speed is saying something is 10 meters per second, we have to be referenced to what, right? So there's two kinds to measure speed. One is called the true wind, and this is measuring speed and direction with the ground as a reference. Right? So with Earth as reference, this is speed and direction. Right? But of course, our blades are rotating system. The blades themselves are not stationary with respect to the ground, right? Where the blades are rotating with respect to ground. So the speed we want to look at is often the relative speed or the apparent speed, meaning that the speed you see when you are referenced to the moving blades. Right? So that's sort of the speed often we care about. So that's called the relative speed or apparent speed, to distinguish from the speed you get when you reference to Earth, right? When you reference to sort of flat Earth. Okay. So now we have to look at some vectors because we're talking about this kind of speed. So you look at vectors, basically, we have the airplane wing or the airfoil has some motion, right? Has some velocity. Then if you look at the, right, so this has some velocity. Then what we care about is sort of the relative velocity. And the thing to make things slightly easier, we'll think of V as the velocity of the airfoil, right? So if you look at this situation, when the airfoil is moving in the opposite direction of wind, so if you look at this situation, right, when the airfoil is moving in the opposite direction of wind, then we have a larger apparent speed, right? We have a larger relative speed, right? So this relative speed is larger because they're moving opposite directions, right? So relative to each other, this is sort of faster speed. Okay? Right? So this is like two cars moving to each other, right? Faster speed. But so to make the sign convention easier, we often flip it around. We'll flip V around and create a variable called h. And h is the head speed, which is just minus v. which h is just minus v. So if you look at this case, what we write is the relative speed is the speed of wind minus the speed of the minus the velocity of the airfoil, right? Taking direction into account. Taking direction into account. Right, so this is vectors. So they have this vector is right. So if they're moving in opposite directions, this is a large number. But this minus sign is a little bit difficult to use, right? So in conventions, we want things to be positive. Right? We want to add things. Then we create this variable h, the head speed, as negative v. Okay? So we can add them. The relative speed is the speed of wind plus h, okay, instead of minus v. Right? So this is the convention we use. So this could be a little bit confusing if you directly look at some of the equations, but the idea is, we basically want to say if wind and h are large, then the relative speed is also large. Okay, so this is conventional dot. Any questions with this convention? Okay, right. So this convention, then let's look at more detailed calculations once we have this convention. So if they're not exactly right aligned with each other, then we need to do vector addition. Okay, we need to do vector addition. So for example, if this is these different colors. So let's say this is wind, this is the true wind speed. Then let's say h as the right? So the head speed relative to ground, W as the wind speed relative to ground. Then if you add them up, we get a vector like this, right? So the relative speed is a vector like this. Okay. So when we were looking at this kind of addition, it's still important to remember this is a vector addition. Right? So they're both a magnitude and a direction, right? And both of them creates a relative speed, So again, this is a true wind speed, or true wind should be called a velocity, but it's in literature, it's conventional called a speed. This is a relative speed, and h as the head speed. So this is the vector addition we have. Then if you look at this for a wind turbine, right? For wind turbine, the idea is if you look at how the turbine is turning, it's always rotating the same plane. Right? It's always rotating the same plane. So this h we have is quite constrained if you look at the relative wind speed to a turbine. Because if you have an airplane, then this h can be sort of three-dimensional and arbitrary. But for a wind turbine, everything is basically kept in the plane of rotation. Okay, so we'll use this sort of picture, vector addition, and adapt to a turbine. We'll adapt to this turbine. All right, so if you adapt this to the turbine, basically, if you look at how the turbine moves is, the velocity is always perpendicular to the turbine, right? So since it's in the same plane of rotation, then this v is always going in one direction, right? You can think of the v going upwards. And this v can be fairly easily computed. So you can compute how fast the blades are going by looking at the rotational speed multiplied by the length, right? By how long the speed is. So the linear motion, this v linear motion, is the product of how fast the blade is spinning versus how long the blade is. And we know we can always say this thing is pointing upwards because there's only one direction this thing can point. So we have is, this is rotation. RC is basically length. Right, so this creates this sort of vertical linear movement, V. And now we can look at the relative speed with respect to this upward motion V, right? We can look at this sort of with respect to upward motion V. Because if you look at the wind, right, you have a wind turbine, Wind is blowing towards the wind turbine, and this thing is moving up. Right? This thing is moving up. So our picture is we have wind coming in. This gets added to the, so this is the true wind coming in. Relative to the ground, you can think of the head speed of the turbine blades is always moving downwards. So this is our relative wind speed. Okay, so when we talk about especially when we talk about the angle of attack, it's always respect to the relative wind direction. The reason we compute this is angle attack is not well defined. It's not defined with respect to the true wind, right? It's not respect to the ground. It's defined with respect to the relative wind direction. So when we're doing the control, it's important to know what the relative wind direction is. And the reason we create this relative direction is that the sort of up and down movement of the blade itself comes into this vector addition. Right? Any question about this? Okay, so it's important to remember if you're given a question that give you wind speed or wind direction, then it's important to figure out which wind are we talking about. Are we talking about the true wind or are we talking about the relative wind direction? So let's do an example on this. So let's do an example. Let's say I have a true wind speed. I have a true wind speed of 50 meters per second and the angle of 20 degrees respect to the horizontal plane. So horizontal plane is the ground, is Earth. Then I have a blade, right? I'm looking at the center of gravity of this blade as 20 meters from the hub and rotating at 20 RPM. So what we want is we want to know what is, right, the relative wind, right? Not the true wind, but what is the relative wind direction. Okay, so this is the question. Okay, so what we have is, right, so let's say this is the horizontal plane. We have a wind that's coming this way. Right, if I wind coming this way, this is 20 degrees at 50 meters per second. Okay. And the blades are moving up in this velocity, this V. So what we want to do is we want to find the H direction, right? We want to find the head speed and then do this, then add them up to get the relative wind speed, right? To obtain the relative wind speed. Okay, so first we need to find V, then we flip the sign, then we get H. So you look at V as the speed of rotation of the blade times how long it is. So this is 2 pi times 20 over 60 times how long it is. So we get 2 pi times 20 over 60 times 20, 41.89 meters per second, right? So this is the upward motion we have. What is the angle of V? Then in this picture, right? Remember we have to do vector addition. So what is the angle of this thing? We're doing vector addition. So relative to the plane, what's the angle? All right, so this thing has an angle of 90 degrees. Angle of 90 degrees is pointing perpendicular up. This is always pointing up with respect to the ground. Then if we want to find the relative wind, I want to find the relative wind speed. This is the true speed plus the head speed h. The true speed we have is 15 angle 20. Then what is the angle for h? And the angle for v is 90 degrees.
Just negative 90, I guess.
Negative 90, right? So you just flip this thing around. This is negative 90. And it's important to know this is a vector addition, right? So it's important to know this is vector addition. So you add this exactly the same way you add two phasors. Okay, so both of these has a magnitude and the angle. Right? So your calculator or your computer should be able to add vectors together to each other. Okay, so you add this two, you get 39.37, angle minus 69.02 degrees meter per second. Okay. All right, so the key thing here to remember is you're doing a vector addition. Okay? So it's important to include the angle. Otherwise, the numbers will be wrong. So this is quite common type of problems you see, right? So we can measure speed relative to ground. We know how fast the turbine is spinning. We know how long it is. Then we can find V, we can find minus V as H. You do a vector addition, you find the relative wind speed. Any questions for this?
I have a question. Could you go back 2 slides?
Sure. This one?
So, no, next one.
Yeah.
Yeah. The FL there,
yeah.
Should that be the aerodynamic force rather than the lift force?
Should this be the aerodynamic force? Yeah, I drew FL, yeah, I drew FL in the wrong way. I should draw FL perpendicular with V, actually. Yes. Yes. So after I draw FL directly perpendicular. I should draw FL in direction, same direction as V, actually.
Okay, so
Yeah.
instead, that one would be F, which is...
Yeah, that should be F. Then there's two components. One is FL, one is FD. Yeah, so let me make a note. I'll correct this on the drawing. Yeah, thanks.
Thank you.
To add on to that question,
yeah.
So V always parallel with the direction of FL?
Yes, so we're gonna say V is perpendicular to the ground. I'm gonna pretend the turbines are turning. That's perpendicular to the ground.
Okay,
yeah,
I'm a little bit confused because I understand how V is oriented that when the blade is right there, but if it's at any other point in the circle, like if the blade's headed down on the opposite side of its rotation, is V also pointed perpendicular to the ground at that point?
Right, so this is the case where we say, so let's say your blade's like this, right? So then we're gonna say blade is turning this way. We're gonna say blade is turning this way. And then the angle we care about is this pitch of the blade. So if the air is coming in this way, we're gonna assume that this is, the assumption we make is the rotation is always going upwards. This is sort of the average we're gonna make because you have 3 blades. They're sort of in a uniform, they're all turning around. So each one of them is seeing slightly different things. So to make things simple, we'll average them and say this is going upwards. There's sort of the averaging of the motion.
Oh, okay, cool.
Yeah, so we're not going to integrate over this whole thing. We're going to average this and think of this as the angle. Okay, good. Yeah, so I'll correct the drawing. Okay. All right, so this is the angle of attack, right? So the problem with angle of attack is you have to know the relative wind speed, right? So angle of attack means you have to know the relative, you have to know the wind speed, which is not often, you may not have this very accurately, right? It depends on whether we can measure wind speed accurately or not. So there is often what we do is we create an angle called pitch, which is beta. So beta is the pitch angle. Beta is pitch angle. So pitch angle is the complement of alpha, right? It contains the same information as alpha, but instead of measuring it to the relative wind speed, you measure it to the sort of this vertical motion. Okay, so you know, right? So you know this is turning this way. So you know sort of which direction the blade is pointing to. So you're going to measure it relative to this sort of this direction perpendicular to the blade. Okay, so this is called the pitch angle. So this saves us from talking about the angle of attack, okay, which is referenced again to the relative wind, which we may not know, but where the pitch angle is much easier to compute because it's now relative to the blade, to the rotating blade that rotating in a circle. Right, so if you look at the blade, you basically create this vertical line, and the sum of the angle between your vertical line and the relative wind is alpha plus beta. And we're going to take beta to be the complement of alpha in this case. We're going to take beta to become an alpha. Okay, so turns out to be much easier to talk about beta, to measure beta than alpha. All right, so then the idea is you can increase beta to reduce alpha and vice versa. So this is, there's no new information, but this is a useful idea to have. This is sort of an easier way to calculate. Right, so the reason this is easier to calculate, right? So let's look at one example, then talk about why it's maybe easier to compute. Why it's easier to use in practice. So again, we're gonna continue with the previous example. Okay, I have a 50 meter per second wind and angle 20. This is the true wind speed. If the pitch angle is 5 degrees, we want to know what is the angle of attack. Angle of attack. So from the last example, right, we'll compute this angle, right, 69.02 degrees. So what is this angle, right? So what is the 69.02 degrees angle? So if you look at this angle, what we have is, this is the vertical line. This is 90 degrees. This is the horizontal plane. This horizontal plane. Then the relative wind speed creates an angle of 69.02 degrees. Okay, so this angle is 69.02 degrees. Okay. Then, if you look at the turbine, if you look at the blade design, the blade is designed in such a way that this is 69.02 degrees. And the rest of the angles, the rest of 90 degrees is partly alpha, partly beta. Okay, so together they make up the rest of the angle. So the relationship we have is 69.02 degrees plus alpha plus beta is 90 degrees. Okay, so the total angle to the horizontal direction is 90 degrees. We know the relatively wind direction. And then we know then if we know beta, which we can know by measuring the relative pitch angle, then we can find the angle of attack alpha. Okay, so this is alpha is just 90 degrees minus 69.02 minus beta, so we get 15.98 degrees. Okay, so this is our angle of attack. Okay, so if we know the pitch angle, we can figure out the angle of attack given the relative wind angle. Okay, so so again, beta contains no new information. Okay, it's not a given alpha or beta is equivalent to each other. So then why did I say beta is easier to use in practice? Or why in practice, when you look at wind turbines, you always hear pitch control. You never hear this angle of attack control. We always talk about the pitch of the blade. Right? So if it contains no new information, why do we only talk about pitch in practice? Right? Why is it easier to use in practice?
Is it because the angle of the wind can always be changing?
Can always be changing, but sure. But then that means right? So you normally when you change the angle of attack, you change the lift. Which means that if you, right? So this means if the angle of wind changes, then at the same beta, the lift can change, right? So it's not as if one pitch angle will correspond to one lift or one power generation. So why is that useful? So how do we use that? Right? Why is beta easier to use in practice? You're close, it's close. Idea is, right? So the idea we want to use beta is following, right? So in practice, let's say you have a turbine and want to track a constant power output. Okay, so once track a constant power output. Then if the direction of wind changes or speed or the angle changes, then power output will change, right? Power output will change. But what you can do is you can slowly change beta, try to match, right? Try to sort of adjust your power output to go back to the nominal output. Okay? But normally we never say, given this power I want, compute beta. It's more of a tracking problem. As the power is changing, because the angle of attack is changing, because the angle of wind is changing, then you adjust beta smoothly, right? You adjust the beta to track either at the same power output, or let's say you want to change power output, you can change beta around. You can try to change beta around. So that's why beta is easier to use. We fix the reference point, and we always say, okay, if I change beta, I know I'll change the power output. And then I can slowly change beta to track the power output I want. Right? So that's a tracking problem. Whereas if you talk to the angle of attack, then it's harder because the angle of attack is referenced to the relative wind. Right? So the angle of attack may jump around depending on the wind direction. Whereas beta is easier to think of as a control variable. You're controlling beta to track power output. So that's sort of why it's easier to think about when you're using the wind turbine in practice. So both are equivalent, but in practice, when the turbine control, we just almost always talk about the pitch angle instead of the angle of attack. Okay, so any questions about this example? Okay, so this is the, right, so this is looking at pitch to extract different amount of lift force, torque, and power out of it. Okay. So we always have one coefficient, right? We have this coefficient of lift. But this turns out we want to have another sort of coefficient of performance, right? So if you look at this coefficient of lift, what this coefficient does is to say, if you know the aerodynamic force, then this coefficient of lift relates that force to the force on the blade, to the lift force on the blade. But then that requires us to compute what the aerodynamic force is. Right? We have to compute that force on the blade, which is, may not be that easy. So the next we'll look at another coefficient called coefficient of performance, which says, if you measure the speed of incoming wind, then I want to multiply the speed of incoming wind gives you the power in the incoming wind. I want to multiply this power directly by a number. I want to multiply this just by a number to get the power I can output. Okay, so you don't want to go through this force calculation, then torque, then power. You want to say, can we summarize this whole thing in one number? I measure upstream wind speed. I know the upstream wind power density. Can just multiply by one number to get the amount of electric power I can generate. And so that's what we will do next. Right? So that number will capture everything we talk about here. Okay, and the reason we want to talk about pitch and forces, as you'll see later, sort of this coefficient of performance depends also on pitch. Right? But our goal is to sort of summarize everything, put everything into one number and do that calculation. So again, the idea is if you know the wind speed upstream, upwind, now we know the power density upwind. So I want to find some number or some scaling factor, Cp, where the amount of power, the power of blade, so Cp times power in the upward wind. Okay, so our goal is to figure out this one number, right? If we somehow get this number, then our power calculation becomes simpler, right? We can sort of skip some of the steps in between. Okay, so this number both has to do with the turbine design and has to do with the change in wind speed. It has to do with this sort of changing speed. Okay, because one way to view how much power you extract from wind is through this basically conservation of energy, right? So you can view the wind turbine as some system in the middle. Then if you measure how much kinetic energy there is in upwind, subtract how much kinetic energy there is downwind, then the difference has to be the kinetic energy captured by the blade. Right, so this is the sort of conservation of energy equation. Okay, so let's see what this conservation of energy equation implies for us. Okay, so these are sort of, basically this is an assumption we'll have to make, right? The upwind is faster than downwind because the blade is capturing energy. Okay, so this air moves slower after passing the turbine, after passing the blade of the turbine. Okay. All right, and then to figure out how much, right? So how much power went into the turbine, then let's went into the blade. Then again, we'll look at sort of how much, what's the mass of air passing through this? What's the mass of air passing through this? So we think about sort of a chunk of air going through this whole system. We'll capture this by a mass flow rate. Okay, mass flow rate is basically how much air is going through the blades per unit height, right? How much this thing is going through. So what we have is the mass divided by time we're looking at. This is the flow rate. And this is the area, how big the area is, times the speed, times the density of air. Right? This is one equation we have. Okay. Then for the density of air, we'll just take it to be 1 for simplicity, right? So we almost, for this, 1 is not a bad assumption at all. So this is the mass flow rate. And we'll assume this mass flow rate is constant. Okay, so air is not being lost in the system, right? So whatever this chunk of air comes to the blade, goes through the blades, generates some power, then comes out on the other side, the same amount of stuff, right? This constant flow rate, we're not losing air molecules in the process. Okay, so this is our mass of air. then this will give us some equation basically relates to the speed, relates to each different speed. So what we know is, if you look at this mass flow, what we know is this is constant. Constant mass flow rate. So this is AU times, so this is the area upwind times the speed upwind. This is the area of the blade times the speed at the blades. This is area downwind times the speed downwind. Okay, so this is the important assumption we'll make. We'll make the assumption that this is constant. This is constant flow rate. And this constant flow rate turns out as an important idea, because if you look at this kind of equation, right? If you look at this equation, you will think that the way to maximize, the amount of wind you can extract is basically when the downwind speed is 0, right? If you look at this equation, I have some kinetic energy in upwind, some, subtract the kinetic energy I have downwind. That's the power captured by the blade, right? Then from this kind of equation, looks like to maximize the power captured by the blade, you really want the downwind speed to be 0, right? To maximize where the energy goes, right? And this seems to imply to capture most of the energy, you should build a wall, right? Basically build a wall, stop all the air. There's no air flowing down, right? There's sort of no downstream energy, right? Turns out that's not true. Okay, turns out that's not the case. Turns out the power is not maximized when the downwind speed is 0. That's sort of a little bit counterintuitive. You would think that's the way you extract maximum power. Turns out that's not the case. Okay? So we'll stop here today, but next class we'll pick up from here, and then we'll look at how do we extract power, right? So what is the relationship that relates the speed to the coefficient of performance, and relates, tells us what sort is the maximum amount of power we can extract from the system. Okay? So we'll do that next time. So again, a reminder, homework is out due next Wednesday at midnight. Right? So please take a look, right? Let me know if you have any questions. Right? Then I will see you guys next week.
Thank you.
Thanks.
Thank you.